Is it on? Can you hear me on the back? Good morning, everyone. Well, I was expecting you Said would be next, so. But thank you again for being a chair, and thank you, Ortwin, for hosting all of us here in Dublin. It's a wonderful city. I really fell in love, especially with all the sun around. Thank you for arranging that as well. I am Alexandra Boltaseva from Purdue University, and I have a privilege and honor to be chairing this very first plenary session on the 16th edition of the conference. Meta is a special event, and it has a special place in my heart and many hearts of our colleagues. I think because here at Meta, a lot of things are happening, not only on scientific front, but also connecting with friends and colleagues. And I still remember the very first in Marrakesh with all the colorful thing around us and bazaars, and looking forward to traveling around the world with the Meta to come. So this morning we are opening the plenary session with a distinguished speaker and distinguished scholar from Nanjing University, Professor Ruwen Peng, a specialist and world leader in nanophotonics, plasmonic, metamaterials, photonic transport, and we are very much looking to the first plenary lecture.
Thank you very much for the nice introduction. I'm Ruwen Peng from Nanjing University. First of all, I'd like to take this opportunity to thank the organizer for organizing this wonderful conference. Today, I will talk about our recent work trying to show the Metasurface as a platform for the classical and the quantum light control. This is the outline for my talk. First, we go to background. It's well known that Metasurface can efficiently manipulate the amplitude, phase, polarization, OM of and the other degree of freedom of light wave at the subwavelength scale. They have facilitated various applications in photonics and information technology. For example, in the optical image and the display, optical computation, and clock, and even the 3D lithography. Due to their excellent performance, very recently, Metasurface has already extended from the classical system to the quantum regime. For example, Metasurface can be applied in the quantum source by integrating meta-lens and nonlinear crystals. We can achieve the high dimensional and multi-photon quantum source. Metasurface can also deal the quantum entanglement using the dielectric PP phase metasurface. The people can achieve entanglement between the spin and the OM. The metasurface also can do the photon manipulation. Shown here, a non-unitary metasurface can control the photon-photon interaction from the bosonic bunching to the fermion bunching. Actually, the metasurface can also carry out the quantum state construction and the quantum state tomography with high efficiency. The metasurface even can do the quantum age detection and act as the quantum logic gates. Very recently, Professor Capasso's group has developed a metasurface quantum graph for generalized hormonal interference. All those examples show metasurface already enabled for the quantum photonics and the quantum devices. Today, I'd like to talk about our efforts made on the polarization manipulation from classical to quantum. We start from the geometrical scaling-induced phase modulation. We call it GSR phase modulation in the classical system. It's well known, as we know, by rotating atoms, the PP phase can be generated. due to the easy fabrication, in the metasurface design, people usually use the PP phase. However, there exists intrinsic restriction of PP phase. That means the PP phase add to LCP, I mean the left circular polarized light, the phase angle is -2 theta. While the PP phase add to right RCP, I mean the right circular polarized light, the phase angle is 2 theta. That means LCP and RCP can be is dependent each other. In order to break this restriction, several schemes has been developed. In our case, we do instead of rotating atom, we expand or shrink the metal atoms only. Then we can generate geometrical scaling-induced phase with this. We call it GSR phase. With this GSR phase modulation, the RCP and the LCP can be independent. Then with it, we can simultaneously generate the arbitrary assembly of the polarization states. Physically, when the light illuminates the metal atoms, those atoms actually can add nanoantennas that radiate with certain phase modulation. Then the interference led to multiple diffraction beam. Then the radiating field and the diffraction field satisfy these equations. We can represent it in matrix. If we do the matrix inversion, then we can start from the desired diffraction field and get to know the radiation field we should have. Then that means with this we can do the inverse diversion of the metasurface. Shown here, we can use the GSR metasurface to generate only one circular polarized light. We can also generate the 4 beams, that is a combination of linear polarization states. We can also generate the several beams with the linear polarization and circular polarization. All this is calculated one. Let me show you the experiment. This shown here is the SME image of one of our samples. With this, as the metasurface, we can generate 2 linear polarization states and 2 circular polarization states. Based on the GSR phase modulation, we can also encode with different polarization and decode it with the analyzer. That's in the classical system. Let's move on the quantum system. We try to use GSR metasurface for quantum information process. Actually, with the dielectric 2 PCF GSR metasurface, we can realize the multi-channel distribution and transformation of polarization entangled photons. Shown here, the polarization entangled photon pairs pass through 2 PCF GSR metasurface. One photon goes through the first metasurface and generates M channel. The other photon goes through the second metasurface and generates the N channel. Then totally we have M by N channel of polarization entangled distribution and transformation. That's the principle. Let me show you some results. First, we did 2x2 entanglement distributors. We fabricate 2 pieces of metasurface, which has 2 polarization channels. Then the polarization entangled photon pairs interaction with 2 metasurface. We have totally achieved 4 Bell states. Shown here is we carry out the quantum state tomography and reconstruct the density matrix showing the high fidelity. We also did the S parameters. All the S parameter is higher than 2. Then we also did the measurement of 2 photon polarization interference features. The visibility is over 71%. This is the first example. Then we did 4x4 entanglement distributors. We fabricate two pieces of metasurface. Each has 4 polarization channels. Then the polarization entangled photon pair interact with these 2 metasurface. Eventually, we have 4x4, 16 polarization entangled states shown here. All of them show the high fidelity and also have a strong polarization correlation. That's our experimental results. That means by developing GSR phase modulation, with the metallic GSR metasurface, we achieved simultaneously generate arbitrary assembly of the polarization states. Then we try to go from the classical to quantum system. Then with a piece of dielectric GSR metasurface, we realized the multi-channel distribution and the transformation of polarization entangled photons. I'd like to say here, with the microscaled dielectric metasurface can efficiently decrease the number of conventional, the bulk weight and optical components. If in contrast quantum network, we expect this approach can pave the way for the future integration of the quantum information process and network. Very recently, with a piece of metasurface, we realized interference-induced entanglement engineering. That means with piece of GSR metasurface, we generate the polarization entanglement and achieve multiple channel distribution. Let me show you very briefly the 2 unentangled identical photons, differing only in polarization, are incident on this metasurface. This metasurface has n channel, and at each channel, supports a specific polarization transformation. Then the metasurface facilitates 2 photon interference on the metasurface, then generate post-selective CN2, n by n minus 1/2 polarization entangled states, and forming a fully connected entanglement distribution among each 2 output channels. That's the brief principle. Then we did experiment. Shown here is the silicon metasurface fabricated by E-beam lithography. Then we did the single photon experiment that demonstrates their multi-channel capability. Actually, this metasurface has 7 channels. At each channel support a specific the specific polarization transformation. That's the single photon experiment. Then we laid 2 unentangled identical photons, the differing only in polarization. For example, with the HV incidence on the metasurface, then our experimental demonstrates we can generate 4 Bayer states and distribute 21 channel by this metasurface, single metasurface. Actually, we are showing here is the reconstructed density matrix showing the high fidelity. Also, we measured S parameters and 2 photon diffraction interference features. This is the HV incidence. Then we change the incidence to be AD incidence. Then our experiment demonstrates we can also generate the 4 Bayer states and distribute to 21 channel pairs by the same metasurface. Actually, the distribution of the 21 channel is different from the HV incidence. That means our approach can offering the flexibility in generating polarization entangled photon pair, but only by adjusting the input photon states. This is one hand. The other hand, the distribution of the polarization entangled states can also be modulated by the changing the assembly of the meta atoms in the in the unit cell. That means the number of the output channel can be further increased. For example, shown here is the simulated results with a piece of GSR metasurface. We can generate 13 output channel, and then the number of the channel pairs can jump to 78. That means our approach can enhance the capacity of the capacity and also the flexibility of full connected quantum network architectures. This approach actually can provide a compact and practical platform for high-capacity communication in quantum information process. This work is published in this year, and very fortunately is selected by the become Edison suggestion and featured in physics. Then let's come to a single metasurface can carry out the multi-protocol quantum key distribution. With PP phase metasurface, with the polarization entangled photon pairs interact with this metasurface. Then, due to the spin-opto conversion, then we can achieve multiple spin and orbital angular momentum hybrid states. With these hybrid states, we can operate the QKD such as the BB84, BBM92, and the E92 protocols, and even can be extended to other protocols. Let me very briefly show the experiment. We fabricated the silicon metasurface. This metasurface has 4 channels. Then the incident polarization entangled photon pair interact with this metasurface, then produce 4 spin and angular momentum hybrid states. Then 2 of them, we use the 2 of them to operate BB84 protocol, and the other 2 perform the BBM91 protocols. Shown here is the experimentally measured probability of the detection matrix. All those experiments demonstrate we achieved the high secret key rates and the low quantum bit error rate. I'd like to say here the single metasurface supports the multiple QKD. As we know, the different QKD actually can offering the varying strengths against the different attacks. With this, with the single metasurface supports multiple QKD actually can combine their advantage to enhance the overall system's security. unlike the conventional bulk, lossy optical system, our metasurface for the multi-protocol QKD actually can offer advantage, at least in size, weight, and power. They have particularly useful, for example, in the limited the system such as satellite system or the large-scale system such like a city network. Next, I'd like to go back to the classical system and try to show you break the limitation of polarization multiplexing in optical metasurface with engineered noise. The polarization can be applied to do the multiplexing technique and transmit the information through the different channel to the different desired target, which can be applied in optical communication, information description, and data storage. The metasurface recently has been applied for the polarization multiplexing. Actually, they can describe in geometrics. Then, shown here, the people use the two orthogonal linear polarization to do the two functionality. Actually, they rely on the diagonal elements in geometrics. If used not only a diagonal element in geometrics, but also add the off-diagonal element in geometrics, then the channel number can be increased to be 3. However, due to the dimension restriction in geometrics, there exists a fundamental limit of polarization multiplexing in the metasurface. I mean, with the single layer metasurface, the polarization channel number is limited to 3. However, if we can break this limitation, it will be crucial for developing high-capacity technique. Let me show you our recently we break this limitation with engineered noise. We want to design a metasurface which has M polarization channel. At each channel, we can do for example, the hologram, optical hologram, and show the holographic image. Then the unit cell of metasurface contains several rows, which can act as nano antennas. If we have only one channel, then the optical response satisfies these equations. If we have M polarization channels, this equation can be extended to this form. Then, if this equation has M solution, then we can get M polarization channels. However, according to linear algebra, these equations is overdetermined linear equations. They have only the principal solution only if M less or equal to 3. That agree with the previous work. Then, in order to get more than 3 polarization channels, we do not use the principal solution. Instead, we use the approximate solution. For example, we consider the linear square solution, then the deviation between the approximate case to the ideal case, we can define the correlated noise. Actually, with this correlated noise, we can create new polarization channels. Let me take M equal 4 as an example. Suppose we want to show the different, four holographic image at 4 different polarization channels. That's the target. If take conventional one, the first 3 channel works well, but the fourth channel is the superposition of first 3. But if in our case, the fourth channel is quite different from the for the other three. That means we indeed create new channels. Actually, we have to admit there exists, but at the same time, we bring out some crosstalk among the channels. Then in order to eliminate crosstalk, we add non-correlated noise. For example, the random noise. Shown here, by increase the intensity of random noise, we can eliminate the crosstalk will gradually disappear. That's the strategy. Then with this approach, we actually can get the upper limit for the polarization channel number could be increased to be 11. Shown here, the 11 different holographic images can be generated from this piece of metasurface. Actually, this limit can be increased further if we release the threshold conditions. I like to mention here our approach can be combined with other multiplexing methods. Shown here, it can be combined with positional multiplexing. In this experiment, with a piece of metasurface, we have 4 positions. At each position, we have 9 polarization channels. Then totally, we have 4 by 9 and 36 holographic image, including 10 digital and 26 letters for the miniatured optical keyboards. Our approach can also combine with OM multiplexing. This is the calculated one. In this piece of metasurface, I mean the calculated result, we have 4 polarization channels. At each channel, we have a polarization channel. We have 5 OM with the different topological charge. Actually, our approach can combine with other multiplexing technique. Very recently, we're based on a multi-dimensional optical response equation from the near field to the far field, which we can do the hybrid multiplexing of polarization, wavelengths, position, and OM. Shown here, we did the hybrid multiplexing of polarization and wavelengths that show the world love our mat. And we also did the hybrid multiplexing of polarization, wavelengths, and OM. Actually, currently, we did experiments at a visible regime. It definitely can be extended to other bands and other waves, including the infrared, terahertz wave, microwave, and something like that. With this, we can say add noise could for better multiplexing. With this, our approach here is particularly useful for achieving high capacity optical display, information repurchasing, and data storage at a miniatured system. Let me have a summary. With those examples, we show the metasurface play unit role not only in classical light manipulation, but also show great potential for advancing quantum information technology. This work is done in my group and Professor Muang's group in Nanjing University. For the multiplexing, we cooperate with the Professor Yongming Liu at Northeastern University in the United States and Professor Lai Yun in Nanjing University. For the quantum work we did in Nanjing University, we get financial support from NSF China and most of China. Thank you for your attention.
Thank you very much. It's a wonderful, wonderful opening for the conference to see that the area of nanophotonics and specifically metasurfaces is now expanding for the ongoing, to impact the ongoing quantum information technology revolution. We are ready for some question, and there is a question.
Hi, very nice talk.
Thank you very much.
I'm curious if you have some sort of results or maybe even intuition as to, for your last section, maybe something like the scaling of the contrast for your output with maybe the spatial frequency of your target outputs, and maybe also with the number of target outputs.
You mean the GSM phase modulation?
Yes.
Yes. Actually,
this is the optical, the multiplexing.
Multiplexing.
Yes.
Yeah. In our, I mean, in our. I mean, the first, initially, we only consider one frequency, I mean, the one wavelength. Then we try to, at that time, we focus on the polarization multiplexing. We consider only one wavelength. That is, the first example is about, is at 700 nanometers. But then we try to combine the optical to the polarization multiplexing with the other, I mean the other techniques such as the wavelengths. Then that's in this experiment we actually did only two wavelengths. One is the 700 nanometers. The other is the 850 nanometers. Anyway, with this approach, we can also to further extend the wavelengths, the number of wavelengths. But right now, we get this one. Thank you.
I see. I guess more my question was like the complexity of. Oh, okay.
Anyway, we can discuss later.
Sorry, then maybe you can take it in the break.
Yeah, thank you. I would just have a quick question about the polarization entanglement manipulation. I was wondering, what do you mean by a channel in this case? Is it related to the K vector of the outgoing light? And